Hi there and welcome back. Today's video covers all of Chapter 3 of Essential University Physics by Wolfson. My name is Jason Harlow. Here we have an outline for today. We're going to start off with Section 3.1 on vector math, then velocity and acceleration in 2 dimensions. We'll get on to relative velocity, constant acceleration in x and y, and a very good example of that is projectile motion, which has constant acceleration in the y direction. And then lastly, motion on a circular path, section 3.6. And you can see there's the penguin. Wolfson asks the question, at what angle should this penguin jump in order to maximize the distance he travels out onto the ice there? We're going to answer that in this video. Okay, so let's start by talking about vectors, and in particular how a vector is different from a scalar. So a quantity that is described by a single number is called a scalar quantity. Example would be mass, temperature, volume. All of these, you just give one number. You could type it into your calculator, for example, and it would completely describe the quantity. A vector is something that has both magnitude and direction. The geometric representation of a vector is an arrow, such as the one that I've drawn here. We have a particle which is traveling at some velocity v. The name of the vector is this v. The magnitude is 5 meters per second, and we would draw a longer arrow for a greater magnitude. And then the direction of the velocity is specified by the direction of that vector, or that arrow that you draw. There are other, I guess the 3 main vectors we deal with in this chapter are position, which usually gets the letter r, velocity, which usually gets the vector v, and acceleration, which usually gets the vector a. Okay, so I mentioned that position is a vector, so let's give an example of that. Suppose you walk 2 meters in a direction that is 30 degrees from the x-axis. So if you define the origin to be the position you were, I guess, originally at, then now we have this vector r1, which is your new position. And we can even write that r1 is equal to 2.0 meters, and you could say 30 degrees, for example, maybe north of east. So the origin was some earlier position. Now your position is 2 meters 30 degrees north of east, where the y-axis is north and the x-axis is towards the east. So we'll put x there and put y up like that. So then you turn right a bit and walk an additional 1.0 meters parallel to x. So now your final position can be found as r2 here equals r1 plus delta r. So r2 is your final position, r1 is your initial position, and delta r is your displacement. And the displacement definition of displacement delta r is equal to r2, your final position, minus r1, your initial position. Okay, so when you're adding vectors, I'll discuss 2 sort of geometric methods of doing it, and then we'll talk about components. So it's usually convenient to draw all your vectors with their tails together. Here is figure A showing a vector E going up and a vector D going to the right. If you want to find the sum of those 2 vectors, F equals D plus E, one way you can do it is called the tipped tail method, which is you slide the vector you want to add over to the head of the vector you're adding it to, and then start from the tail of the first vector and extend it up to the head of the second vector, and that is your sum, F equals D plus E. The parallelogram method is where you keep the vectors both starting from the same place, and then you draw a parallelogram using those vectors, and the sum is the diagonal across the parallelogram. Either way gives you the same result. If you want to add more than just 2 vectors, this is an example of using the tip-to-tail method for adding vectors d1, d2, d3, and d4, all of which are displacement vectors for this hiker. First he hikes down here, then turns and goes up there, and down and back up. The net displacement is found as d1 plus d2 plus d3 plus d4. So let's talk about components. If you draw a vector on the xy axis, say the vector A as shown, then you can always find components of A, the y component and the x component. So for example, if you already know, let's look down here, if you know the angle theta and you know the magnitude A, then A sub x, the x component, is A times cosine theta, as drawn here. The y component, A sub y, is A times sine theta. So that's if you know the magnitude and direction, you can find the components. If we look up here, it shows you the equations for if you know the components. The magnitude turns out to be the square root of the sum of the squares of the components. You find that from Pythagoras there. That's a right angle. And the angle in this case is the arctangent of A sub y divided by A sub x. So that's one example. Here we've got an angle phi showing this vector b. In this case, looking down here, if you want to find the components, the x component is now b times sine phi, which you can just look at the equation or look at the graph and see that. And then the y component in this case is actually negative b cos phi. So these minus signs get inserted manually depending on this the direction that you see there. And then looking up top, if you already know the components, the magnitude once again is always the square root of the sum of the squares, and you have to look at the diagram to find this angle phi, which in this case turns out to be tan to the minus 1 of b sub x divided by the absolute value of b sub y. So now that we can find components of a vector, we can more easily add or subtract vectors, or even multiply them by a scalar. So if d is a plus b plus c, then d sub x is a sub x plus b sub x plus c sub x. So you just add all the x components and you get the x component of the sum. Similarly, you add all the y components and you get the y component of the sum. Very, very easy. And the nice thing about these components is they can just be added on your calculator because they're scalars. If you want to subtract two vectors, r equals p minus q, you just subtract the components. So r sub x is p sub x minus q sub x, and r sub y is p sub y minus q sub y. Lastly, you can take a vector and multiply it by a scalar. So for example, if vector t is scalar c times vector s, then all you do is you multiply the components of s by that scalar c to give you the components of t. So lastly, on this vector math section, I want to talk about unit vectors. So these are specified by a little hat. I hat and j hat are the unit vectors in the x and y directions. All they are is just a vector of length 1 pointing in the x along the x-axis or along the y-axis. And this is just a nice way of converting components, writing components to sum up and form actual vectors. You just multiply the x component times I hat plus the y component times j hat, and you get a vector. Unit vectors just establish the directions of the positive axes of the coordinate system. Okay, so when you're talking about kinematics now, two-dimensional velocity can be represented here. So here, I think this blue line is meant to represent a trajectory, but when the particle is at this particular position, it has velocity, which is this green arrow. Well, you can split that velocity into x and y components by using the direction of that velocity. V sub x is v cos theta, and v sub y is v sine theta, where v is the speed, which, if you already know the components, can be found as using Pythagoras. And Also, this theta direction of the velocity can be found by the tan theta is v sub y over v sub x. There's also two-dimensional acceleration. So once again, we've drawn the trajectory, and now you can think about the instantaneous velocity at two moments in time. v1 is the velocity at some time, and v2 is the velocity at some time delta t later. We can use vector subtraction of these two velocities to find delta v, which is equal to v2 minus v1. And then you divide that delta v by delta t, and you get the average acceleration vector. And of course, as you limit delta t, as delta t approaches 0, you get the instantaneous acceleration vector. So on this trajectory, perhaps the instantaneous acceleration might be this way. It doesn't have to be in the same direction as v. And in fact, if a particle is turning, then there's always a little component towards the component of the acceleration towards the inside of that curved path. So by definition, a is the rate at which v is changing at that instant. Okay, so next I want you to consider the velocity of one particle, but viewed from two different perspectives. So the S perspective is the laboratory frame up at the top here. And what you see is velocity, lowercase v, which is going up and to the right. But now there's another reference frame, S prime, which is moving at a velocity to the right in the laboratory frame, capital V. So now if you look below, you will see the S prime perspective. And the first thing you should notice about the S prime perspective is that the velocity of S prime is stationary in its own perspective, and instead what it sees is the S frame as moving to the left with a magnitude that same velocity capital V. And now if you look at the particle, you'll see that in the perspective of S prime, the particle is moving up and to the left. And there's an equation there which is that V prime, the velocity of the particle in the S prime frame, is V minus V. So the velocity in the S frame minus the velocity of the S prime frame relative to the lab. And an alternative to that equation is V without the prime is V prime plus this capital V. Okay, so summing up, if we know an object's velocity measured in one reference frame S, we can transform it into the velocity that would be measured by an experimenter in a different reference frame. And this is called the Galilean transformation of velocity, that V prime is V minus V, or V is V prime plus V. And you can look at that in terms of components, V sub x and V sub y, same equation in component form. And I just want to note that as we go forward towards the end of Physics 132, you will talk about Einstein's theory of special relativity, in which there's the relativistic transformation of velocity, which looks different than this. Okay, let's do an example of relative motion. A jetliner flies at 960 kilometers per hour relative to the air, heading northward. There's a wind blowing at 190 kilometers per hour towards the east. In what direction should the plane fly? Okay, so we'll set S as the ground frame and S prime is the air. So capital V is the velocity of the air relative to the ground. And we're told in the problem that that's 190 kilometers per hour. That's the velocity of the wind. Now lowercase v is the velocity of the plane relative to the ground. That's the desired velocity. Okay, and we're told that we want it to be north. And then lowercase v prime is the velocity of the plane relative to the air. Okay, and this is what is set actually by the steering wheel. This is what the pilot sets. And we're also told that that the magnitude of that is 960 kilometers per hour. Okay, so now we'll use that equation. V is V prime plus capital V. You can see I've drawn that there, drawn the vectors out where lowercase v is straight to the north, the v prime is off to the left a little bit, and then there's that capital V to the east. So there's a right angle right there. We can see that sine theta is opposite over hypotenuse. That's capital V over V prime. You can solve that out for theta is sine to the minus 1 of 190 over 960. That's 11 degrees when you plug that into your calculator. Okay, so it's a long video today. You're only about halfway through. I just wanted to take a quick break and give you the big idea here in the middle of chapter 3. So if the acceleration a equals a sub x times I hat plus a sub y times j hat is constant, then the two components a sub x and a sub y are both constant. And in this case, everything that you learned from chapter 2 about constant acceleration kinematics applies to the components. And the x and y components of the motion can be treated independently. The only way they remain connected is that t is the same for the x side and for the y side. So please keep that in mind as we go forward and do our first application of this, which is projectile motion. Okay, baseballs, tennis balls, Olympic divers, etc. all exhibit projectile motion. A projectile is an object that's moving in 2 dimensions under the influence of gravity only. Okay, so this is vertical plane that it travels in, and the only important force while a projectile is traveling is the gravity force. So projectile motion extends this idea from chapter 2 of freefall motion to include a horizontal component of the motion, but it's a similar acceleration. Air resistance is neglected, and projectiles in 2 dimensions, as it turns out, follow a parabolic trajectory. And this is seen in this nice picture that's showing little droplets of water in a fountain. You can see their trajectory has this curved shape, which is called a parabola. Now, the start of a projectile's motion is what we call the launch. The launch velocity, or initial velocity v sub 0, has an angle above the horizontal of theta sub 0. And so you can break that initial velocity into vxo, like the initial x velocity and the initial y component of the velocity, where v sub 0 is the initial speed. So gravity here is acting downward, and if you define the positive y-axis to be up, then the components of the acceleration are a sub x equals 0, and a sub y is negative g, where g is the this 9.8. Sorry, g is equal to 9.80 meters per second squared that we talked about from free fall. So the horizontal component, a sub x, is 0. Basically, projectiles are in free fall. So, and this is a picture from your textbook showing the trajectory of a particle which starts with this initial velocity v sub 0 right here. What's happening is that if you look down here, v sub x doesn't change. So there's some initial x component of the velocity, v sub x 0, that stays the same from moment 1 to moment 2 to moment 3 to moment 4. So there's actually larger amounts of time between 2 to 3 and 3 to 4 than there are from 4 to 5. But basically it's just moving at a constant speed in the x direction. Meanwhile, in the y direction, what's happening is that it's slowing down. So v sub y starts with this big component, then it gets less, and then it gets less, so that at the top of the trajectory, v sub y is equal to 0. And then, in fact, it continues to accelerate in the same direction downwards. The acceleration vector doesn't change, so that now at time 4 it's moving down, and time 5 it's moving down with the same same magnitude initial velocity in the y direction, but now it's negative. So let's do an example of a heavy ball which is launched exactly horizontally, this is yellow one, at a height h above a horizontal field. And at the exact instant that that ball is launched, a second ball, which is red, is simply dropped from height h. Which ball hits the ground first? Well, if air resistance is neglected, both balls will hit the ground simultaneously. So the initial horizontal velocity of the yellow ball has no influence over its vertical motion. Neither ball has any initial vertical component to its motion, so they both fall a distance h in the same amount of time. So what this is showing here is just that the y component of the motion doesn't affect the x component of the motion, or vice versa. Range of a projectile. So we started off this video looking at a little penguin and asking what's the angle that the penguin should jump at to maximize the range. So a projectile with some initial speed v sub 0 has a launch angle, it should say theta sub 0, above the horizontal. How far does it travel over a level ground before it returns to the same elevation from which it was launched? This distance is sometimes called the range of a projectile. It is derivable in the textbook. X equals v sub 0 squared over g times sine of 2 theta. And what's shown here is actually the trajectories of a projectile launched always with the same initial speed of 50 meters per second, but at different initial theta sub zeros. 15 degrees, 30 degrees, 45 degrees, 60 degrees, and 75. So if you launch it at a low angle, it hits the ground really soon. If you launch it at a high angle, it has a large hang time, goes in the air for a long time, but if you go too high up, it just doesn't have as much x component of its velocity, so it doesn't go as far. And it turns out the maximum angle, or the maximum range, happens at an initial launch angle of 45 degrees. So that's the answer for the penguin. Okay, so last section is circular motion. This is just another example of motion in 2 dimensions. And I'm going to start by asking you to think about a ball on a roulette wheel. So there's a groove which forms a circular path along which the ball must travel. Okay, so that's an example of circular motion. You can also think maybe of a satellite going around in a circular path around the Earth, or maybe a ball whipping around on the end of a string. In all these cases, there's an object that goes on a path which goes in a circle. So to begin with, we'll think about uniform circular motion. That is when something's going on a circular path at a constant speed, and the circle has some radius r. So if we look at the picture here, the velocity is tangent to that circle, and all the velocity vectors are the same length. The time interval that it takes to go all the way around, we might call that the period, capital T. If you wanted to find the speed from the period, you would do the circumference divided by the period is 2 pi r over t. So that is the speed of uniform circular motion. So next is centripetal acceleration. So in uniform circular motion, although the speed is constant, it's still accelerating because the direction of the velocity vector is always changing. So for example, up here at the top of the path, the instantaneous velocity is to the left. If you wait for a while, there's some angular velocity there I'll talk about later called omega. The velocity vector has now changed. It's now down and to the right. And so since there's this continuous change, there must be this continuous acceleration, which we call centripetal acceleration. And it turns out to be constantly changing as well. It's always directed towards the center of the circular motion if the speed is uniform. And the magnitude of the centripetal acceleration is constant for uniform circular motion. So if you want to find out what that is, you can look at the velocity v1 at one instant and v2 at another instant. By definition, a is dv by dt. So you can take delta v is v2 minus v1. This turns out to be a similar triangle to delta r, which is r2 minus r1, because they have the same angle. We can do the analysis and find that the magnitude of that acceleration at any instant is v squared, where v is the instantaneous speed, divided by r. And the direction is towards the center of the circle. If the ball is maybe speeding up or slowing down, if you think a real ball on a roulette wheel, it's not just going around at a constant speed, it's also probably slowing down. So that means that the acceleration has both radial and tangential components. So the acceleration is a sub r plus a sub t. There's the magnitude of the acceleration is going to be the square, because those are found by Pythagoras, because those two components are perpendicular. A sub r means that's in a radial direction perpendicular to the velocity, and a sub t is in the same direction parallel to v. So for example, if a car is turning and also slowing down, then what's happening is that there's a component a sub r, the centripetal, and that's going to be a sub r is equal to v squared over r, and where v is this instantaneous speed. And there's a sub t is the tangential, which doesn't have an equation for it, but it's just saying that they've got the brakes on, they're slowing down. Those are the two components which together form the actual acceleration, which is often this diagonal. It's neither perpendicular to the motion nor tangential, and that is equal to a sub r plus a sub t. So I will see you in class.